Yesterday we have learned about KVL, and using this KVL we solve different numericals on transistors. Then we started diode. In the diode we did series and parallel combination. Then we started doing about Jenner diodes, right? Fine. So this is what we have learned in our last session. In today's session, what we will do is we will continue with diodes and Jenner. Then we will solve op-amp, operational amplifier. And I will try to solve as much as numerical as possible. Okay, so let's start.
Yes, sir.
Okay, fine. So this is the circuit. So this was asked in GATE 2013. So it is saying that in the following circuit, the voltage drop across the ideal diode in the forward bias condition is 0.7. The current passing through the diode is. This is what they are asking. That is, they are asking you to find the current flowing through this. I will call this one as ID. That is the current flowing through the diode. Okay, so suppose if I take this current to be I, then this current, can I say I minus ID? Is this okay? Yes or no? Can I say it like this? If
Yes, sir.
I is a current, I can divide this one as I minus ID and ID. See, sometimes you can use this one as I2, but it is unnecessarily creating, means introducing more variables. Whenever you name the current, you should name in such a way that you will have minimum number of variables. So in this case, how many variables are there? Two unknown variables. One is I and one is ID. So the question is asking you to find ID. So what we have to do is, since there are two variables, we need two equations to solve these two variables. So how to get this equation? Anyone? KVL is the trick, right? One loop, you can take it like this. You can take this loop, the outer one. Yes. And another one, you can take this loop. So I'll call this one as A and this one as B. Okay. Now we have two loops, loop A and loop B. So now for the loop A, can someone tell me the equation? Anyone?
24
Very good.
minus I 12 kilo ohm
Okay.
minus ID 3.3K.
Okay. What about the voltage drop across the diode? Will you not consider that one? Because here it is given 0.7 volt, right, in forward bias condition.
Minus 0.7 volt.
Yes. Good. Then this is equal to
0.
0. Now, can another person say for loop B? Yeah, you can also try. The same person. Sorry, I am not able to see your names here. So, yeah, anyone? Anyone?
Minus 0.7.
Minus
0.7.
0.7.
Minus 3.3K ID.
3.3K ID. Then
Plus I minus ID.
I minus
into
ID into
6K.
6K. Very good. So now we have got two equations, right? Equation 1 and equation 2. So if you see this equation, this is a linear system of linear equation. Now, can you solve? Yeah, now we can solve equation 1 and 2, and you can find out I and ID. Yes or no?
Yes, sir.
Yes, sir.
Can you do? Yes. So this is a trick. Now you can see the simple KVL, Kirchhoff's voltage law, which you have learned in the beginning. It is useful in many electronics numericals, right? Okay, have you understood this one? Shall we move on to next question?
Yes, sir.
Yes, sir.
Okay. Now, what about others?
Are waiting there. வந்துட்டு
Sorry?
and it இது எலக்ட்ரானிக்ஸ் பார்த்துக்க சூப்பரா இருக்கு எலக்ட்ரானிக்ஸ்
Okay, sorry, I'm not able to.
லூப் ஏ எப்படி பண்ணியது லூப் பி நல்ல யூஸ்ஃபுல்லா இருக்குடி மற்றல உள்ளதான் அப்படிதான் இருந்துச்சு
Okay, can someone translate it for me? Actually,
அந்த
I do not
லாட்டிஸ்
Tamil.
ஸ்ட்ரக்சர் எல்லாம் இருக்குல்ல அதுல இருந்து நம்ம அந்த இதுகள் கண்டுபிடிப்போம்ல கிளாஸ் ஆனா சூப்பரா எடுக்காது
Hello?
So they
It
unmuted.
seems somebody unmuted their mic, sir.
Okay, technical team, can you please unmute the... Okay. Okay, fine. Okay, so we move on. We will move on to next question. Yeah, this is the question. It was asked in GATE 2020, right? So, okay. Now tell me, I will call the three diodes as D1, D2, and D3. Fine. Okay. Now, please tell me whether the three diodes will be forward bias or reverse bias.
Forward bias.
Forward bias. Good. So if it is forward bias, I can just replace this circuit like this. Because in the question itself, they have given that all the diodes, the voltage drop is 0.7, right? So this one is 10.1 volt, 1K, 0.7, 0.7, 0.7. Fine. Now, once this is done, in the question, they have asked what is the current flowing through this 1 kilo ohm. You have to find out. So can you apply KVL here? Yes or no?
Yes, sir.
Okay, tell me the equation. Anyone?
10.1
10.1
minus I into 1K
minus I into 1K.
3 into 0.7.
Okay, 3 into 0.7 is equal to 0.
To 0.
So from this, you'll get I to be 10 minus 2.1. Sorry, 10.1 minus 2.1. So the answer is 8. It is milliamp because that resistance is 1K, right? So this is the answer. Solve. In just 1 to 2 lines, you can solve this one. So this was asked in GATE 2020. Any problem? Any doubt?
No.
Are you able to follow this?
Yes, sir.
Okay, so we move on to next question.
Yes, sir.
Okay. Now this is very interesting. Now see, don't get panicked by the graphs and by the circuit. What you have to do is you just have to focus on the basic principle. How a Jenner diode function. That's it. Right. Now, if you see this, now first you try to focus on the circuit. So basically, this is a input and the input signal goes through 500 ohm and there is a Jenner diode here. And in parallel to this Jenner diode, we have a 1 kilo ohm. Now, see this, the input is connected to the N terminal of the Jenner diode, right? And the input current is shown here. This is the input current. And what they are asking, which of, okay, I'm not showing you the options here, but the question is asking which of the following waveforms shows the current I passing through the Jenner diode. So this is the input. This is the input. And what we are interested is, we are interested to find out I, which is the current flowing through the diode versus time. This is what we are trying to find. Okay. And in the question, they also have given that the Jenner diode has a breakdown voltage of 5 volt. Yes or no? Right? Are you able to follow me?
Yes.
Okay. Now, so Vz is given to be 5 volt. Now, when the input is less than Vz, what will happen to the Jenner diode? On or off?
Off.
Off. But when V input is greater than or equal to Jenner diode, what will happen? Jenner breakdown will happen. And what is Jenner breakdown? Let me draw the graph again here. The graph, the breakdown will happen like this. So this is at Vz. This is what I'm referring to. This is what I'm referring to as a breakdown. So in the breakdown, large current can flow through the diode, but the voltage will be around Vz only, right? So this is the concept. Now, in the input, now, okay, this is not current. I think there is a mistake here. This is a voltage. This is the voltage, V in. And if you see the graph, let us try to divide at 5. Because this is 5 volt. If the voltage is greater than 5 volt, then Jenner will be in breakdown. But if it is less than 5 volt, then it will be off. When I say Jenner diode is off, it means it is open circuit. Yes or no?
Yes.
Yes. Okay. Now if I try to map this one, approximately, let us try to map. This one is coming to 1, and this one is coming at 3, and this one is coming at 5, and this one is coming at, let's call it 7. Fine. Okay. Now let us try to plot this graph. 0, 1, 2, 3, 4, 5, 6, 7, and 8. So from 0 to 1, the input voltage is greater than Vz or less than Vz?
Less.
Less than
Less.
Vz.
So if it is less, then it will be open circuit, right? Yes or no?
Yes, sir.
So if it is open circuit, what will be the current flowing through the Jenner diode?
0.
0.
0.
0.
So yes, so the graph will be like this, 0. But from 1 to 3, from here to here, the voltage is greater than Vz. Yes or no? Yes. So
Yes, sir.
whatever the current it is supplied, it will go here like this. Yes. What about from 3 to 5?
Open circuit.
Open circuit. So the current will be 0 here. What about from 5 to 7?
Breakdown. Xeno breakdown.
General breakdown. So whatever it is supplied, it will occur like this. So the graph will look like this. And what about the magnitude here? What is the peak value? Okay. No, this peak value is fine. So, okay. Now, can you see the pattern of the current here?
Yes, sir.
Okay.
Round out.
Yeah.
So there is a difference between VI and the voltage across the inner diode, no, sir. In between there is 500 ohm, no, sir. So we have to find.
Sorry. You are saying that
Sir, the
VI.
voltage across the Zener diode should be greater than 5 volt, no, sir. In between
Yes.
VI and there is 500 ohm. There is a contradiction.
In between what? Can you please repeat it again? I'm not
In
able to
between
get you.
VI, input voltage V and the Zener diode, there is 500 ohm. No, sir.
Okay, there
Will be
is
some drop.
500 ohm. Yeah. Okay, nice. I understood what you're trying to say. Uh, Normally, when we design a voltage regulator, we put a resistor here. We never connect a Zener diode or a normal diode directly. This is just to protect the diode without altering the flow of the current. Can you understand? If you see the value here, the value is less, right?
Okay, sir.
And I can understand what you are trying to say. You are saying that, sir, because of this diode, because of this resistance, will there not be some change in the current or the voltage?
Yes,
That is what you are trying to say, right?
yes.
Yeah. That there will be some minute changes, but for this question, we are not considering that one.
Okay, sir.
Okay. But I think you can get the gist of what how I'm trying to solve this question, right? I think you can get
Yes,
the
sir.
gist of what I am trying to explain, how to tackle such kind of problem, right? Okay, now, shall we move on to the next question? Okay, so this question, I have not drawn the diagram. Let me draw the diagram first. And it was asked in CSIR UGC NET 2017. So I will give you some few minutes. Please read the circuit. In the meantime, I will draw the circuit diagram. I think this is a circuit diagram, and the supply voltage is 10 volt, and we have a 1K, this one, and D1. The current flowing here is ID1. Current flowing here is ID2. This is diode D2, and this current they are calling as I1. Okay, this is the circuit. So the question is asking find the value of I1 plus ID1. I1 is the current flowing through the 1 kilo ohm, and ID1 is the current flowing through the diode D1. Fine. Have you understood the question?
Yes, sir.
Okay. Now, how to tackle this? Let us apply KVL. Apply KVL. Okay. How to apply? Suppose now let's see. See, sometimes even if you know the concept, if you do not apply in proper places, you'll find it difficult. For example, I will give you a demo. Suppose if I take this loop, I'll call it loop A. If I take this loop, how many variables will be involved?
Two variables.
Yes, two variables. Suppose if I'll write it down here, if I take loop A, I have two variables. That means to solve this equation, you need one more equation, right? Yes or no?
Yes, sir.
But if you take this loop outside, I will call it loop B. How many variables are involved?
One.
Why not ID2?
Two.
Okay, here is the tricky part. Because since D2 is forward bias, the voltage will be 0.7. Yes or no? Yes.
Yes, sir.
Then
Sir.
in that case, the KVL will look like this: 10 minus I1 1K minus V0 is equal to 0. From here, can you find out I1? Yes or no? Are you able to follow this?
Loop A also
Sorry?
same equation only comes.
Yeah, it's same. Yeah, fine. But the thing is, you have to find out ID1, but you have to find out ID1 also, no?
Diode
Okay.
is forward bias.
Yes, same. Yes, fine. You are correct. So what is the value of I1? 10 minus 0.7 by 1K. So this comes out to be 9.3 milliampere. Now, in the question, they have written that both diodes are of the same characteristic. That means you can take ID1 is equal to ID2. Yes or no? Can I
Yes,
say
sir.
it like this? So since ID1 and ID2 are equal, so I1 plus ID1, this one I can write as I1 plus I1 by 2. Can I write it like this? Because I1, it is divided in equally in both the part. Yes, because ID1 is equal to ID2, it is equal to I1 by 2. Yes or no?
Yes, sir.
Yes, sir.
So from this equation, can I write 3 by 2 I1? Yes.
Yes, sir.
So the answer is 3 by 2 into 9.3 milliampere. Yes. It's okay now?
Yes, sir.
Okay. Any doubt till now? Okay. Shall we move on to next topic?
Yes, sir.
Okay. Now I'm going to analyze first the remaining 1 hour. We will be discussing around 10 to maybe 15 questions on op-amp. Right. I'm going to discuss around 10 to 15 numericals on op-amp. And the interesting part is, this is the interesting part. The interesting part is, I will be teaching you only two concepts. Maybe I can't say two. I will be teaching you very few concepts, maybe 2 to 3 concepts. And by using this concept, you will be able to tackle almost 15 types of problem in op-amp. So why I'm saying you this is, the next 10 to 15 minutes, please try to focus it. try to understand what I'm explaining. If you have any doubt, unmute your mic and say, sir, can you kindly explain it again? I'm ready to explain it, because whatever I'm going to teach you in the next 10 to 15 minutes, that is, those concepts are very important, and with those concepts, you can tackle maximum numericals on op-amp. Am I clear to everyone?
Yes, sir.
Okay. So if you are not able to follow it, unmute your mic and say, sir, please repeat it again. I will be very happy to repeat it again. Okay, so op-amp. Op-amp is nothing but it is operational amplifier. I'm not going to go to the basic one. What op-amp is used for, what are the means, what are the characteristics, what are the compositions, what are the block diagram. I'm not going to those details now. I'm straightway teaching those concepts which will be helpful to solve the numericals. That's it. So whenever you see an op-amp, you have two terminals, one denoted by minus and the other denoted by plus. So this, I'll call it V1, V2, and V0 is the output. And sometimes they will show the power supply also, like this, suppose 15 plus 15 or minus 15 V, right? So whenever there is if the input is given at the minus, this minus is what we call as the inverting terminal. Inverting terminal. And the plus is what we call as the non-inverting terminal. So, so what is inverting terminal and non-inverting terminal? See, I'm explaining this because you need to have an idea. Okay, this is inverting, this is non-inverting. Suppose if I ground the non-inverting and if I give an input at the inverting, then what will happen is, if you supply a signal here like this, then the output will be amplified and it will be inverted. That is why we call it the inverting terminal. Fine? Yes?
Yes, sir.
Suppose if we ground the inverting and if we supply an input, then what will happen is, suppose if you supply a input like this, the output will be in the same phase, but it will be amplified. Means the phase will be the same with an amplification. Fine? Yeah. But you will, now this is the interesting part, because some of the numericals in GET and NET, they see this basic characteristic and they try to twist the question so that the students can make mistake. But the interesting part is you will not be getting an output like this, because the gain, the voltage gain of the amplifier is of the order of 10 to the power 5. Can you understand this? This is the voltage gain. So 10 to the power 5 means, suppose if I give 1 millivolt as an input, then what will be the output? 1 into 10 to the power minus 3 into, okay, let me write it properly so that you can follow. The output will be AV into V input. So what is the gain here? 10 to the power 5. What is the input here? 10 to the power minus 3. So how much voltage you are getting?
100 volt.
100 volt. But 100 volt is not possible because our supply is how much? 15 volt. Can you understand this one? The output
Yes, sir.
cannot exceed the supply voltage. There is one GET question where they have asked this one, because if you calculate like this, it is exceeding. So the output, the maximum output should be greater than or less than the supply voltage. It cannot be more than the supply voltage. So if you give 1 millivolt as the input, the output will look like this. The output will saturate like this. Can you understand? And this one will be V saturation minus V saturation. Saturation means the maximum output voltage that the op-amp can give. Fine. Are you able to understand this? Okay, let me repeat it again. So if I give 1 millivolt, the output, if I calculate, it is coming 100 volt, but this 100 volt is more than the supply voltage. So what will happen is the output will get saturated at some maximum voltage, and V saturation means the maximum attainable output. And this is close to the supply voltage. Fine. Okay. Now, so to avoid this, see, can you see any feedback here in this circuit? Can you see any feedback here?
No,
Yes
sir.
or no? So such kind of circuit is what we call as open loop circuit. Open circuit of op-amp. Right. Now there is one type of circuit known as a closed loop circuit of op-amp. Okay, I'm going to next slide. So let me give you one basic circuit. Minus plus. Can give one input register here, one register here, and the inverting, and here I'll give input. Second. Okay. This is the V0, and this one I'll call it R1, and this one I'll call it RF. So in this circuit, can you see a feedback here? Can you see the output is feedback to the input here through this RF resistance? Hello?
Yes,
Yes,
sir.
sir.
Yes. So this feedback, it is a positive feedback or a negative feedback?
Positive.
Negative.
Why it is positive?
Because it's inverting, sir. So
Yes. See, I am giving the input at the inverting, so the output will be inverted, and the inverted is given as the input, so it will be a negative feedback. Fine. Now, this circuit is also known as the inverting circuit. Okay. Now, please try to listen it carefully. Now I'm going to teach you the concept of virtual ground. By using the concept of virtual ground, you can tackle almost all the op-amp based questions. Please try to focus. If you are not able to follow, tell me to repeat it again. Now, the ideal characteristic of op-amp, there is one point known as the input impedance, means the resistance at the input. It is very high. Ideally, it is infinite. It is very high. Yes. Another is the gain is also very high. Ideally, it is infinite. So this is the characteristic of op-amp. Now, if A is the gain, then my V naught is equal to A into V in. Am I right?
Yes, sir.
And from this, can I write V input is equal to V naught by A? Can I write it like this? Yes or no?
Yes, sir.
But the gain is very high. Since the gain is very high, the input will also tends to 0. Yes or no? Since the denominator is very high, the whole quantity will tends to 0. It will be very small. Yes?
Yes.
Now, here comes the interesting part. Let me draw the circuit here. I'll draw it a bit bigger here so that you can. Now, okay, here is the V in. This is R1, this is RF, and you are grounding the non-inverting. So, since V input is tends to 0, that means we can assume that this point, whatever the voltage here, I will call it Vx. Vx is the voltage which is going to the op-amp. Yes or no?
Yes, sir.
Yes. So because of this condition, which is led by this condition, we can take Vx to be almost 0. Can I say it like this?
Yes, sir.
And this is what we call as the virtual ground. But remember, this is different from the actual ground. How it is different? You must have seen this symbol, right? Grounding symbol. This is the actual ground. But in the actual ground, infinite current can pass through in actual ground. But in the case of virtual ground, can any current pass through it? Yes or no?
No, sir.
No, because the input impedance is very high. Can you now understand the difference between virtual ground and actual ground?
Yes, sir.
Yes or no? Okay. Now, this concept of virtual ground simplifies the calculation of op-amp. It simplifies the calculation of op-amp. How it simplifies? I'll show you now. Whenever you have any type of op-amp circuit, let it be like this. Or like this. Or let it be like this. See, I'm drawing different variants of circuit. Whatever the circuit is, any type of op-amp circuit, whatever the circuit is, can you see this point? Can you see this red dot? Yes? Can you see this?
Yes, sir.
Okay, let me use a laser pointer. Can you see this point?
Yes, sir.
Okay, because of the virtual ground, by default, you can assume that the voltage at this point and the voltage at this point will be same. That is, I will call this one as A, I'll call this one as B. By using virtual ground concept, you can just assume VA is equal to VB. Similarly here, if this is A, this is B, you can assume that VA is equal to VB. Similarly here, this point, I'll call it A, this point is B. Here also you can assume that VA is equal to VB. Have you understood what I just explained? That is a trick using virtual ground. Okay?
Okay, sir.
Okay. Now let us try to tackle this circuit one by one. I will call this one as A. I'll call it this one as B. I'll call it this one as C. Okay, now let us start with A. Suppose you are interested to find the output. How you will find out? By using the concept of virtual ground. See, apply KVL. Apply KVL in this loop. Can you see the loop which I have drawn here?
Yes, sir.
Yes? Okay, now yeah, please try to respond. Audible? Hello?
Yes, sir.
Yeah, see, the point B is grounded, right? So grounded
sir.
means what is the voltage at B?
0.
Zero. It is zero. So if VB is zero, can I say VA is also zero?
Yes, sir.
Okay, now you see this point. Can you see this figure? So if current I is flowing here, then can I write I is equal to V input VB divided by R1? Can I write it like this?
Yes, sir.
Now, the concept which I'm going to explain, this is also very important. What is the input impedance of a op-amp? It is very high, right? Yes or no?
Yes, sir.
So since the input impedance is very high, almost all the current will go through this feedback resistor. Can you understand? It will not be able to go towards the op-amp. It will go to the feedback part. Yes?
Yes, sir.
That means,
Yes, sir.
can I say the same current is flowing through this feedback resistor RF? Can I say it like this? Yes
sir.
or no?
Yes, sir.
So that means, can I write it VB minus V naught by RF? Can I write it like this? Yes or no?
Yes, sir.
Now VB is equal to 0. This is equal to 0. Now from here you can write V naught by V input is equal to minus R F by R1. Yes? Yes or no?
Yes, sir.
So
Yes, sir.
this is the gain. This is the gain of an inverting circuit, right? We'll be using this expression frequently. Okay, now let us. Are you able to understand this one? Because I will be using this. Whatever I have done here, no, I will not be elaborating it. I will be directly writing this expression. So because of that, you have to understand this one, how I'm formulating this equation. Because in the coming numericals, I will be directly writing the equation without describing how I have come to these equations. So, are you able to follow this? Yes or no?
Yes, sir.
Okay, now let us move to next circuit. So in this circuit, I will call this one as R1 and this one as RF. The difference between the circuit A and circuit B is in circuit A, the input is given at the inverting terminal, but in circuit B, the input is given in non-inverting terminal. So what is VB here? Anyone?
Vn.
Very good. So can I say VA is also V in?
Yes, sir.
Okay, now this I will draw the part here. RF, R1, and this is VA. So in this part, if I apply the KVL in this part, the same current will be flowing here, right? Yes or no? See, the current direction can be opposite. I'm just assuming that it is flowing in this part. So from this, let me write the equation. 0 minus VA by R1, it is equal to VA minus V naught by RF. Yes or no? Is this equation okay?
Yes, sir.
Yes, sir.
So this equation, can I write 0 minus V input by R is equal to V input minus V naught by RF. Can I write it like this?
Yes, sir.
Okay, now from here, you can write the gain. The gain is what? V naught by V input is equal to 1 plus 1. Yes,
RF by
anyone?
R.
R?
F by R.
R. Is this the equation?
Yes, sir.
What is VB here? I will call this one as R1. I'll call this one as RF. I'll call this one as R3 and maybe R2, and this one is R3. So what is VB here? VB is the voltage here. So can you apply the voltage divisor rule?
R3 by R1 plus R2 plus R3 into V.
Very good. This one, right? Yes. And this will be equal to VA, right? Can I write it like this?
Yes, sir.
Okay, now you apply the KVL in this loop, the feedback part. Can someone tell me the equation? Zero minus, yes. Please respond because we have to tackle many numericals also. Kindly respond. This part.
VA.
0 minus
VA.
VA by R1 is equal to
VA minus.
VA minus.
VA minus V0 by RF.
R.
So using this two equation, can you find out the gain of the amplifier? Yes or no?
Yes, sir.
Yes, sir.
Yeah. Okay. Now, shall we solve previous year questions now? Now you are in a, if you have understood whatever I have taught, now you can solve most of the op-amp question. I will not say all, but you can solve most of the op-amp questions now. Okay, so we move on to the questions.
Yes, sir.
Okay. I think this is the same question which we discussed, right? That circuit number C. Yes or no? This
Yes,
was
sir.
asked in gate. So what they have done is they have given the expression of the output. This is the expression of the output. And they are asking what is the ratio of R1 by R2. Right. Now, for this question, I will solve in two different ways. Why I will solve in two different ways? Because both the approach are useful. So the first thing, I will use my approach which I have taught. This one I will call it A, this one I will call it B. So what is okay, fine. So here the difference between ours that C circuit is here both input are given V1 and V2. That is the difference. Okay, fine. No issue. Okay. So first you try to find out VB. VB. What is VB here? VB. Yes? Anyone?
R2 by R1 plus R2 V2.
R2 divided by R1 plus R2 into V2. Nice. Good. So this is equal to VA. Is this okay?
Yes, sir. Yes, sir.
Now you apply the KVL in this part, in the feedback part now. Apply the KVL. Yes, anyone? Please.
V1 minus VA
V1 minus VA. Nice.
divided by R
Very good.
equal to VA
Equal to
minus V0.
VA minus V0
V0 R.
divided by R. Yes. Fine. So luckily we are able to cancel this one. And you can write V0 is equal to what? Twice of VA minus V1. Yes or no? Yes.
Yes.
Yes,
Yes.
sir.
Now you substitute this equation, then you will have what? VA. So 2 R2 by R1 plus R2 into V2 minus V1. Yes or no? Yes.
Yes, sir.
Then if you express in the form of R1 by R2, it will be better. So what I can do is I can divide it R1 by R2 plus 1, V2 minus V1. Is this fine? Yes. So now if I rearrange, I can write minus V1 plus 2 divided by R1 by R2 plus 1 into V2. So this is the expression of the output. Now you compare with the expression given in the question. In the question is given as V0 is equal to minus V1 plus V2 by 2. So now you compare this equation and this equation. What is R1 by R2?
3.
3. Very good. The answer is 3. So see, by using the concept of virtual ground, you can easily find out the answer. Out. Okay. Fine. Now, there is another approach which is relatively easy, easy, but yeah. Now, suppose you have 1 and 2. If this is the case with the feedback, actually this is with the feedback, but I'm just drawing a schematic diagram where you can understand. This one you can always see as a combination of like this, minus plus, give the input. This is a schematic diagram. Please try to remember this. This is a schematic diagram. You ground this one. You give input at 1. Let this be V01. You'd sum up this with the other one ground like this. This is just a schematic diagram. I'm repeating it again. V02. Okay, now let me try to explain. Suppose you apply input at both the terminal. Then you can, the net output, you can take as a sum of two output, where in one case you apply the input here, ground the other one, calculate the output. Next, ground this input, you apply the input here and calculate the output. Right. Then you can write the net output as V0 as V01 plus V02. You can write it like this. This is also another trick to solve faster. Yes. Are you able to follow this?
Yes, sir.
Or shall I repeat it again?
Sir,
Okay.
repeat again.
Okay, good. Okay, now please try to see this circuit. How inputs are applied at both the terminal, right?
Yes, sir.
So this is the circuit. This is just a schematic diagram. So input are applied at both the terminal. Then what you can do is you can write the output as a sum of two cases. In one case, you apply the input at 1 and you ground the input at 2. And you calculate the output. That one I am denoting it by V01. In the second case, you ground the one input, and in the second input, you give the supply. Then you calculate the V02. If you sum up these two, you'll get the net output. Fine?
Okay, sir.
Okay. Now, if I ground this one, and if I supply the input here, what is this circuit? Inverting or non-inverting?
Non-invert.
Inverting or non-inverting?
Invert.
Invert.
Inverting. So V naught 1, what is the formula for non-inverting? Minus R by R into V1. Is this correct?
Yes, sir.
You can see here. This is the circuit. This is the circuit, right? The gain is minus RF, the feedback resistance by the input resistance. So I'm writing it here. Okay. What about V02? Yes. Do you want me to draw the circuit here?
Plus RF upon R
Now
into
see.
V1.
Wait. When I ground this one, even though here I am supplying V2, the input which is going to the op-amp is nothing but the voltage here. Yes or no? Yes?
Yes.
So what is this voltage? R2 divided by R1 plus R2 into V2, right? What I'm saying is VB is what? R2 divided by R1 plus R2 into V2. Yes or no? Yes?
Yes, sir.
And this VB is the input which is going at the non-inverting terminal. Yes or no?
Sir.
And the gain of non-inverting is 1 plus RF by R1 into V input. This is the formula, right?
Yes, sir.
So V naught 2, the gain is 1 by R plus R into the input voltage. Yes or no? And this input voltage is nothing but VB. Am I right?
Yes, sir.
So you'll get 1 plus R by R into R2 by R1 plus R2 into V2. Yes or no? And if you sum up, this is nothing but 2 R2 by R1 plus R2 into V2. Now, what will be the net output? Minus V1 plus 2 R2 by R1 plus R2 into V2. Now, you can see that both the expression are same. Okay. Are you able to follow this?
Yes, sir.
Yes, sir.
What about others?
Yes, sir.
Yes, sir.
Okay. So we move on to next topic, our next numerical.
Yes, sir.
Yes.
Okay. Now, this circuit looks very much different, right? To the circuit which we have done before, yes or no? Yes or no?
Yes, sir.
Let me just redraw the circuit. They are giving one V at the non-inverting terminal. They are grounding this one. Then they are giving to R2. And from R2, one is going to the inverting. Then this is going to R1. And this is going to output. And this is the load. Can you see what I have done?
Yes, sir.
Yes, sir.
Now the circuit looks very easy, right? It's the same circuit, but they have drawn in such a way that it looks very much different. Yes?
Yes, sir.
Now, what is this circuit? Inverting. Now, what they are asking, find the current passing through
R2.
R2.
That means they are asking this current, right? Yes or no?
Yes, sir.
Now, what is the voltage at A here? I'll call this A and B. What is the voltage at A?
10 millivolt.
V, right? Yes or no?
Yes, sir.
Yes, sir.
And this is equal to VB by concept of virtual ground, right?
Yes, sir.
So in this circuit, if I apply a simple relation, 0 minus VA divided by R2, this is the current. Yes or no?
Yes, sir.
And this is nothing but minus V divided by R2 is equal to I. And you can find out I is equal to minus, what is the voltage here? 10 millivolt divided by, what is the R2 here?
Okay.
K, 1K.
1
So it
kilovolt.
is minus 10 microampere. Done. But can you see there is a minus sign here?
Yes, sir.
You know why? But I am taking the current direction to be like this, right? From ground to it is going like this. But the answer is coming minus. This means that whatever current direction I have taken, the actual direction is in opposite. That's why the minus sign is coming. Fine?
Yes, sir.
Okay. Minus sign is coming because the direction which I have considered, it is not correct. I have to take the opposite direction like this. That's it. Okay, so we move on to the next question.
Only positive 10 microampere something.
Yes, the answer is 10 microampere. See, in electronic circuit, if the current direction is not given, we assume a certain direction. And after solving it, if the current is coming to be negative, that means whatever you have assumed, you have to inverse the direction. That's it. Okay, so we move on to next question.
Yes, sir.
Yes, sir.
Okay, here I have not drawn the circuit, but let me draw the circuit. In the meantime, please read the question here. This was asked in GATE 2018. Minus plus. This is grounded. And they have given two input like this. And they have given a feedback resistor. And they are taking across RL. This one is 4K. This is 2K. This is 5K. Actually, I cannot remember what is the value of RL, but I think it is not necessary here, V1 and V2. So this is the circuit. Now, this can be solved in many ways, but I will use a trick. Suppose you have two input like this in an op-amp, minus and plus with some feedback resistor. Suppose V1 and V2, and let's say this is R. This one you can break it down like this. First, you give only one input plus the second input. You can break it down like this. This is possible. V2. Yes? Are you able to follow this?
Yes, sir.
So,
Sir,
yes.
sir,
Okay.
this
Now,
is applicable on both inverting and non-inverting.
yeah, means in the previous trick, I have mentioned separately for inverting and non-inverting, right? Hello?
Sir, you said like we can add these voltages. So if the voltage is provided on the positive terminal, then also this is valid.
Yes. But the thing is, you are saying that if it is applied in the positive terminal, right?
Yes, yes.
Yeah, means that summation is possible, but it will also depend on the circuit. But for this case, it is possible. Like V1 and V2 is applied at a negative terminal. You can separately find out the output and you can sum up. That is possible. And
Okay.
if you want to know the reason why, because if this is I1 and if this is I2, right? All this current are flowing to the 4K ohm. So you can separately analyze. That's the trick. So if now, if only V1 is applied, what is the V naught? It is inverting amplifier, right? Minus 4 by 2, 4K 2K into V1. Yes or no?
Yes, sir.
I'm
Yes.
using this formula. V naught by V input is equal to minus RF by R1 for inverting amplifier. I'm using this formula. So KK cancel. So minus 2 volt. Yes or no? Yes. Are you
Yes.
able to follow this?
Yes, sir.
What about others?
Yes, sir.
Yes, sir.
Okay, now if only V2 is applied, then V naught 2 will be equal to what? Minus of 4 divided by 5 E2. This is how much? Minus 8 by 5 volt. Yes, which is nothing but minus 1.6 volt. So what is the net input? V naught 1 plus V naught 2. Yes or no? Yes.
Yes, sir.
So it will be minus 2 volt plus, sorry, minus 1.6 volt. It is minus 3.6 volt. This is the answer. Okay, I would like to inform you that basically this circuit, it is a summing amplifier. This circuit is a summing amplifier. That's why I'm able to write it like this, because both the voltages will sum up. That's why I'm writing it like this. Okay, shall we move on to next question? Hello.
Yes, sir. Move on, please.
Yes, sir.
Okay. Please solve this question. So this circuit is what? Inverting or non-inverting?
Inverting, sir.
So V naught is equal to minus 100 R divided by R into V input. Yes or no? Yes.
Yes, sir.
So R cancel. What is V input here? 100 into
1.5 volt.
1.5 volt. So what is the answer here? 150 volt. So which option is correct? A, B, C, D.
D, option D.
D.
So actually minus sign is missing.
Okay, minus is missing. Fine. They are asking only the magnitude. See the question, only the magnitude. So what is the correct answer? A, B, C, D.
C, sir.
D.
C. It cannot be 150. Why? Because the supply voltage is 15 volt. So it cannot exceed. So it will saturate at 15 volt.
Okay, sir. Okay, sir.
This was asked in GATE 2019. Okay, I'm moving on to next question. Yeah, now things will become more interesting. Till now, we have been dealing with passive component, but solely limited to registers. Yes or no? Whatever op-amp circuit which we have discussed till now, we have been limiting ourselves to the register, right? Now, this was asked in GATE 2020. Now, you can see that there is a capacitor. Although the form of the circuit is almost similar to what we have discussed before, but there is an additional, like instead of resistor, there is a capacitor, right? Now, whenever there is a capacitor or inductor, use this relation. Instead of means when we were dealing with resistor, we were replacing with the resistance, right? R1, R2, RF. Whenever there is a capacitor, just replace it with XC, right? Now, I will give you a minute to read the question. Please read the question carefully so that I can proceed with the explanation. All of you, please kindly read the question once. Okay, have you read the question?
Yes, sir.
Yes, sir.
Okay, so what it is saying is the input voltage is 2 cos 100t volt. So here 100 is omega because we write sine omega t, right? And the output is 2 cos 100t minus pi by 2 volt. So can you see that there is a phase difference between the input and the output? Can you see that?
Yes, sir.
Yes, sir.
And what is the phase difference here? Pi by 2 or minus pi by 2?
Sir, both are same, I think.
No, both are not same. If it is plus pi by 2, that means the output is leading. If it is minus pi by 2, then the output is lagging. There is a difference. So here the output is leading or lagging?
It is leading, sir.
Okay, you please find out whether it is leading or lagging. But for now, I will take the phase difference is minus pi by 2. Okay, you can analyze that one graph by using graph. Okay, now let us come back to the circuit. Now, for this circuit, the inputs are given to both the terminals, right? So what I'll do is I'll call this one as terminal 1 and this one as terminal 2. Now, can I find out V01? That is, input is given only to 1 and the 2 is grounded. Can I use that trick? Yes or no?
Yes, sir.
So in that case, V01 will be equal to what? Minus when the
R
in
minus R
minus
into
R
V in.
divided by R into V in. Yes or no? And this is equal to minus V in. Yes? Are you able to follow this? Okay. Now, what about, okay, let me just draw this circuit so that you, for V02, I'll just redraw the circuit so that you will be a bit familiar with this. Instead of this capacitor, no, this capacitor, you can, this is the impedance XC and RC. R, yes, V in. So in this case, the input at the terminal 2 is nothing but the voltage drop across this capacitor. Yes or no?
Yes, sir.
So what is that voltage? What is this V2 here? V2 is XC divided by R plus XC into V in. Yes or no?
Yes, sir.
That means, and the gain of the amplifier of non-inverting is what? 1 plus R by R into V2. Yes or no? Yes?
Yes, sir.
So V02 is equal to RR cancel, twice of XC divided by R plus XC into V in. Now you have got V02 and have got V01. Yes? So the net output V0 is equal to V01 plus V02. So if you simplify, then this will be minus V in plus twice of XC divided by R plus XC into V in. Yes? Now, I can take minus 1, 2. XC I can replace by J omega C, right? R plus J omega C into V in. Yes or no? Yes. I'm using this formula. XC is equal to 1 by J omega C. Hello?
Yes, sir.
Now, you can do the mathematics here. This one, I'll just write it down. You can simplify like this. Omega CR divided by 1 plus J C omega CR. You'll get an expression like this. Right. Now, let me take a new slides. I don't think we have got space. Just 1 second. I'll copy this one and put it here. Yes. I will use this relation. Okay. I will go to next slide. Yeah, this is the important part. Whenever there is a capacitor in the op-amp circuit, then you have to tackle it like this. So the expression was, let me use black pen. The expression was V0 is equal to what? 1 minus J omega CR divided by 1 plus J omega CR into V in. This was the expression. So what I'll do is V naught by V in 1 minus J omega CR. Now see, on the right hand side, the expressions are, they are complex number. So a complex number, we can write X plus I or J, whatever you want to call it. This is one way of writing a complex number. There is also another way of writing a complex number in the polar form. Can someone tell me how to write a complex number in polar form? R e to the power I theta. Yes or no? Yes? So what I'll do is this one I will write in the polar form like this. 1 plus omega CR whole square 1 plus omega CR whole square into e to the power minus j theta and e to the power j theta. Is it fine? You know this, right? Theta. Hello?
Yes, sir.
You know how to write in polar form, right? So that is what I have done. So these two will cancel out. Then you'll get e to the power minus 2j theta. Now, here theta is equal to tan inverse omega CR. Here we use, right, theta is equal to tan inverse y by x or x by y. Hello?
Y by x.
Yeah, y by x. The same thing I have used here. Now, what was the phase difference in the given in the question?
Minus pi by 2.
Minus pi by 2. And this is the, let me use a different color. And this is where the phase information is hidden. And here we can see that the phase difference is minus 2 theta. Yes or no? Yes. So this minus pi by 2 is equal to minus 2 theta. Yes.
Yes,
So
sir.
minus minus cancel. Then you have pi by 2 is equal to 2 tan inverse omega CR. So what was asked in the question? Find the value of C, right? C, find the value of C in microfarad. So we are done here, because from here you can have tan pi by 4 is equal to omega CR. What is tan pi by 4? 1 omega CR. Then you can find out C is equal to 1 by omega R. Omega is how much?
100.
100. And what is R? 1, I think 1 kilo ohm, right? Yeah, 1 K. So 10 to the power 3. So you have 10 to the power minus 5 farad. So this is how much? 10 microfarad. Done. So whenever, if I try to summarize why I included this question, because whenever you have any capacitor or inductor even in the op-amp circuit, you just treat this capacitor as a kind of a resistor whose impedance is 1 by j omega c. And you use the same inverting, non-inverting formula which you have done for the case of resistor. And in the final expression, it will always come in complex number. Whenever it comes in complex number, if you want to find out about the magnitude or the phase, then you convert this complex number in the polar form, then you analyze the circuit. That is how you can deal with a circuit of op-amp which has capacitors or inductor. Fine. Okay, I think it's already time, but I have more question. Maybe later on, if time permits, we can discuss. For example, this one, how to solve this. Even this one also we can solve. Then this one, even this diode also we can solve. And this one also we can solve. But I think 4 more questions are left. Maybe I can give these questions as a kind of a question set, and you can solve it, and maybe we can discuss it later. Fine. Okay. Thank you, everyone.